Hi there, my name is Kunal, and today I'll be explaining what goes on in the top right corner of the SAT formula sheet. Special right triangles. In today's video, I'm going to explain what they are and then go through a few example problems. There are two types of special right triangles. They are the 45-45-90 triangle and the 30-60-90 triangle. The numbers I'm talking about refer to the angles inside of the triangle. Remember that triangles will always add up to 180 degrees. So what makes these triangles special is that these angle combinations within the triangle create special relationships between the side lengths in the triangle. So the lengths of the sides are dependent on how big the angles are. So the bigger the angle across from that side, the bigger that side is going to be. Let's take a look at this example problem to help visualize the concept I was talking about. So this question is asking you to order the side lengths, and this question can be solved by looking at the angles. So the bigger the angle, the larger the side across from it is going to be. So whenever you see a problem like this that's asking about shapes or something you have to visualize, it's a lot easier if you can actually visualize it by drawing it out. So let's do that. We know angle A is the biggest, followed by B, followed by C. So if we draw it, it's going to look something like this. From there, we can figure out the lengths of the sides. Since A is the biggest angle, the side across from it should be the longest, or in this case, side BC. Looking at the choices, we can eliminate A, B, and C automatically because they don't have side BC as the longest. So we can circle choice D and move on. Now that we've talked about how different angle lengths can affect side lengths, let's talk about the special right triangles. And we'll start off with the 45-45-90 triangle. Its shorter legs have a value x, and its hypotenuse, or longest leg, has a value of x times the square root of 2. So this makes sense because two of the angles are the same length. So based on what I was talking about earlier, that means the sides across from them also have to be the same length. So then by using the Pythagorean theorem, you can calculate the length of the hypotenuse as x times the square root of 2. The other special right triangle is the 30-60-90 triangle. The short leg, or the one across from the 30 degrees, is going to be value x. The one across from the 60 degrees is going to be value x times the square root of 3, and the hypotenuse is going to be value 2x. So a quick example here, if we have x be 3, then the legs are going to be 3 times the square root of 3, and 6. Now that you know what the special right triangles are, when are you supposed to apply the ratios? Well, let's talk about it. Here are some common signs. The first one might seem pretty obvious, but it's if you see 30 degrees, 45 degrees, or 60 degrees anywhere within a shape, you're probably going to have to apply the special right triangles in some way. The next one is if you see a square root of 2 or a square root of 3 anywhere on a side length where you could make a special right triangle, you're probably going to have to use it. The next one is the one that's most commonly overlooked, but it's whenever you get an SAT problem that's asking you about a square or a equilateral triangle inscribed within a circle. You're going to have to use the special right triangles to solve those. So let's jump into a few examples. This first example problem is a pretty straightforward example of applying a special right triangle. And it says to consider a right triangle with one angle measuring 60 degrees, and the length of the shorter leg is 6 units. And it's asking us for the length of the hypotenuse. So let's draw it out first. Given in the problem, we know it's a right triangle and one of its angles is 60 degrees. So that means it's the 30-60-90 triangle. So based on this, we know the hypotenuse would be 2 times the length of the shortest leg, or 6 times 2, which is 12. So we know answer choice B is going to be correct. This next problem is an example of an inscribed square problem. We have a square inscribed in a circle with a radius of 5 units, and we're being asked for the perimeter of that square. So let's first try drawing it out. And if you don't know, inscribed just means we're taking that square and we're drawing it inside of a circle with all 4 of its corners touching the outside of that circle. So the angles inside of a square are all right angles, or 90 degrees. So if the radius is 5 units, why don't we multiply that by 2 to get the diameter of 10 units? The diameter is the line in the middle of the circle that divides it perfectly in half. but in this case, it can create a hypotenuse of a triangle. And when we use it as a hypotenuse, we can effectively create the 45-45-90 special right triangle because we're cutting that square perfectly in half along its diagonal, which is also going to cut the 90 degrees in half to 45. So now that we have a value for the hypotenuse, the side lengths of this triangle would be 10 divided by the square root of 2 based on the relationship we know of the 45-45-90 triangle. So now that we know the length of one side, to find the perimeter, we can simply just multiply this by 4 for all 4 of the sides, giving us 40 over the square root of 2. But wait, you'll notice that's not an answer choice. In fact, none of the answer choices are divided by a square root. And this is because on the SAT, answer choices are always in rationalized denominators. This is when you have a root in the denominator and you get rid of it by multiplying your fraction by the denominator over the denominator. In this case, to rationalize it, we would multiply 40 over square root of 2 by square root of 2 over square root of 2. And we can do this because it's still giving us the same number we had before, just in a different form. We're essentially just multiplying our original expression by 1 as square root of 2 over square root of 2 is equal to 1. The process of rationalizing the denominator is just a way to simplify our expression. Now, by starting this process, we'll end up with 40 times the square root of 2 over 2, and further simplifying it, we get 20 times the square root of 2, which is answer choice B. Thanks for watching today's video. I hope you learned something new about the SAT math section and are now ready to kill it on the exam. For more practice problems like the one in the video and access to a 24/7 online study tool, check out ACEIT at the link below. ACEIT is the ultimate study tool for the SATs and the ACTs created by Juni Learning, an award-winning educational tech platform that has helped thousands of students take their learning to the next level. Get a 1-week free trial when you use the link in the description. Until next time, and good luck studying!